both of them react with halogens. Of these two, only one of them produce optically active molecules. The other one does not. Okay, guys? When we do halogenation, one of the diastereomer produces optically active compounds. The other one does not. Now the question is, which one? And I have to tell you, in organic chemistry from now on you will see, when we are doing reactions only for the purpose of diagnostic, to say, for example, if I want to know whether there is carbon-carbon tie bond, we will use boron, not chlorine or iodine. We will use boron. For this experiment, except, again, when I want to find out which of the two compound will produce optically active molecules, I use boron, not chlorine or iodine. Why is that? When it comes to reactivity, in this case as purely, it is difference maybe in second, maybe. They all are reacting so fast that it is difficult to measure rate of reaction. So why bromine is more preferable. Chlorine is poisonous gas. Iodine is solid. Again, all of these are harmful anyway. But that's why you are using a little bit very dilute acid and iodine solution when you have wounds, guys, because they kill the bacteria. But that is very, very low concentration, very small quantity. So, bromine is liquid. Because it is liquid, it is easier to handle. This is one. The second, I don't know, have any of you have seen bromine to know what color it is? When it comes to bromine, it is a kind of, I will say, brownish solution, and that's what it is, really. Brownish, purplish solution. But when you get hollow alkane, it's clear colorless. And this is, I don't know if you have done your unknown or not, in lab, the very first experiment we do to find out whether there is carbon-carbon tie bond adding the bromine solution. If your compound has tie bond, the instant that bromine touches your compound, guess what? Color disappears. So that tells you you have tie bond. Now, that being said, now the question is, how can I find out which of these two will produce optically active, which one does not? Then, again, I'm going to tell you something that I said the other day. Remember the other day I said, we understand these are planar sp2 hybridize, no stereochemistry, flat as pancake, hybridize. But for the purpose of understanding of the reaction, we can use our imagination, which is truthful. What do I mean? Can we go over here? You are not using it, so it's better. Thank you. So, this is my molecule. Is that right? It is flat as pancake. Can I assume that I am looking from this angle? Or from this angle? Yes? Can I do that? Why not? Yeah, no, I'm saying molecule doesn't change, but you can look from one day. See, if you are looking and you were drawing, wouldn't you show, guys, wouldn't you show these bonds are coming towards you? And the ones that they are coming toward me, wouldn't you show that? So even though it is flat, for the purpose of understanding, I can use that. So I would assume that when it comes to this molecule, so you get the idea, you are looking from the other side, is that right? And when it comes to that one, again, if I am looking, so here now I am adding boromine. So obviously boromine is going to be added n-type, is that right? So they have to be 180 degrees apart. Now I'm writing my CH3 because I'm going to ask you. Okay. Assign R and S and tell me whether this compound is optically active or inactive. What is the stereochemistry of this carbon? What is the stereochemistry of this carbon? Is it optically active or inactive?
Not active.
It's not active. It is
Inactive. Oh,
no, you are correct. It's inactive. That's what would you call it? What is the compound that it has stereocenters? Stereocenters, because obviously it has two stereocenters. It's not optically active. Meso. Okay. So this one, as you can see, is meso optically inactive, which you can guess. What is the stereochemistry of this one? Yes. Agree? So if you have RR, what else would you expect? SS. Don't forget, again, I repeat. Because I have written this way, couldn't I put VR there, which gives me SS? So keep in mind, I said, if you are generating a stereocenter and your molecule is not meso, you would expect either diastereomer or enantiomer. In this case, you would expect enantiomer because that is not any pre-existing. So this is as far as halogenation. Now, let's look and understand halogenation one more time. When it comes to halogenation, as you see, we do the reaction in 2 steps. Is that right? Step 1, we are adding electrophile. What do we do in the next step? We are adding nucleophile. It is 2-step reaction. It's not 1-step concerted reaction. What it means that when it comes to halogenation, the halide is not the only nucleophile I can add. I can add a whole bunch of nucleophiles, such as water, alcohol, you name it. Any nucleophile, guys, any nucleophile that you have seen in CHE118A, you can add here. By that I mean cyanide, azide, a different halide. For example, one has chloride, the other one bromide. Okay, guys? So basically, I can make it regioselective as well by mix matching. So, the fact that I can use different halide, one of those that is very, very popular in organic chemistry, one of those nucleophiles is, believe it or not, water. So what I mean, you all know, both in industry and organic lab, epoxides are very popular. Mother Nature does not make epoxide. So how epoxides are being made? Going back to our CHE118A, guys, do you know how to make epoxide? So I give you going back to CHE118A. Do you know how to make ethers? It is a very well-known, named reaction. What am I talking about? Williamson ether synthesis. Have you heard that? Okay. Of course, in case of Williamson ether synthesis, you would take your alcohol, you will change it into alkoxide, you will take a second molecule of alcohol, you would change it into haloalkane, then you would under SN2 condition. When we are saying under SN2 condition, what do we mean, guys? Could your R be tertiary? Absolutely not. Primary is preferable. Secondary, if you have no choice. Absolutely never tertiary, because you are going to get elimination.